You are sitting on a plane. Somewhere beneath your feet, inside those wings, there are up to 180,000 liters of fuel. And that fuel, the thing keeping a 500-ton machine in the air at 40,000 feet, is basically the same liquid people used to light oil lamps 150 years ago. Not gasoline, not diesel, lamp oil. And when most people hear that, their reaction is always the same. That makes absolutely no sense. Most people assume aviation switched to kerosene because it is more powerful than gasoline. The truth is the exact opposite. Kerosene was chosen because gasoline is too dangerous to use at altitude. And here is exactly why. At cruising altitude, roughly 10,000 meters above sea level, atmospheric pressure drops to about 26% of what it is on the ground. At that pressure, liquids behave very differently. They evaporate faster. They turn from liquid to vapor at much lower temperatures. Gasoline evaporates aggressively under these conditions. As it evaporates inside the fuel lines, it creates vapor bubbles. Pockets of gas inside what should be a continuous flow of liquid fuel. Engineers call this vapor lock. Imagine drawing water through a straw that has air bubbles trapped inside it. The water stops flowing smoothly. The suction breaks. The flow stutters and stops. Now imagine that straw is the fuel line feeding a jet engine over the middle of an ocean. The engine stops. At 40,000 feet. That is why gasoline was rejected. The second reason is fire safety. And the numbers here are alarming. Gasoline has a flash point of -43 degrees. That means at almost any temperature a human being has ever experienced. A gasoline is already producing vapors that can ignite from a single spark. A small electrical fault, a bit of friction, anything. Kerosene has a flash point of between 38 and 72 degrees. You have to actively heat it before it produces enough vapor to catch fire. There is a famous demonstration in aviation education where an instructor drops a lit match directly into a container of jet fuel. The match goes out. The fuel does not ignite. Now consider that a long-haul aircraft carries up to 100 tons of this fuel. If that fuel had the ignition characteristics of gasoline, any small leak or electrical fault could cause a disaster that no safety system could contain. Kerosene does not just reduce fire risk. At this scale, it is the difference between a manageable emergency and an unsurvivable one. The third reason surprises almost everyone. At cruising altitude, the outside temperature sits between -50 and -60 degrees. The wings where fuel is stored are directly exposed to that cold. Most common fuels, including many grades of diesel, would begin to solidify at those temperatures. Wax crystals form. The fuel thickens. Flow slows. An engine that cannot draw fuel produces no thrust. Standard jet fuel is specifically engineered to remain fully liquid at temperatures as low as -47 degrees. Special additives prevent wax crystal formation. The molecular structure is refined to maintain flow at temperatures that would turn most other fuels into gel. And here is the part almost nobody outside aviation knows. Before jet fuel even reaches the combustion chamber to be burned, it is routed through passages running alongside the hottest sections of the engine. Temperatures there exceed 1,000 degrees. The cool fuel flowing through absorbs that heat and drops the temperature of critical metal components before they can overheat and fail. The fuel cools the engine on the way in, then burns to power it on the way out. Two completely separate jobs, simultaneously. No other commonly available fuel can do both reliably under these conditions. Kerosene was not chosen because it was familiar or cheap. It was chosen because nothing else could do everything the job required. From oil lamp to jet engine, the same liquid, a completely different world. If this changed how you think about the engineering around you, hit like and subscribe for more. Thanks for watching.